Hello and welcome to Lecture 4A on Assembly Modeling. In the previous lecture video set, we discussed mechanisms such as levers and cams, with a focus on gear train design. We also learned the basics of gear design in Inventor, but if we want to model a complete gear train, we have to learn about assemblies. In this video, we will talk about assemblies, starting with a description of what they are, followed by a consideration of assembly degrees of freedom and constraints. So far, we've learned about modeling single parts, but the application of solid modeling on its own is limited since very few devices are made of single parts. Instead, many products consist of multiple components that must be assembled together. This is essentially what assemblies are. Assemblies are a collection of parts or subassemblies that are put together to make a fully functional device. In the context of computer-aided design, assembly modeling is a process of defining the relationships between all of the components and/or subassemblies to arrange them as desired. Consider this door hinge, consisting of three components, two hinge plates and the pin. To get a functional door hinge, we know that the knuckles of the hinge plates need to be aligned along their axes with the pin inserted to interlock the two hinge plates. So these are some of the relationships that we would have to define in assembly modeling. To make sure that we are all on the same page moving forward in this video, let's define some terminology for assembly modeling, and we can consider this gear train assembly to help. So with assembly modeling, we will call each solid model that is part of the assembly a component, and in an assembly, it is possible to have multiple instances or copies of a component. For example, in this gear train, we have four components: a gear, a pinion, a rod, and a mounting bracket. And in the assembly, we use two instances of the pinion component and three instances of the rod component. Another important term to be aware of is associativity. A feature of Autodesk Inventor is its associative design, meaning if you go and change a component's geometry in its part file, all of the instances of that component in your assembly will be updated as well. This can be handy, especially in iterative design, when you might be updating parts and you want to see those updates reflected in your assembly automatically without having to redo them. Earlier, I used the term subassembly, which is essentially an assembly that we place within another assembly, and usually that subassembly has a particular purpose within the overall assembly. Here we have a complete gear train consisting of two subassemblies, the first being the spur gear train and the second being the worm drive, both of which contain several components. When assemblies are modeled in this fashion, we end up with an assembly tree hierarchy as you see here, with the overall assembly at the top level, and working our way down, we increase in detail until we get to the individual model components. This model tree hierarchy can also be defined as parent-child relationships. For instance, the overall assembly is the parent to the subassemblies, and the subassemblies are considered its children, and these relationships determine how constraint relationships between components will be represented. We won't worry about this too much, but I do have to define what I mean by constraint relationships between components in the context of assembly modeling. Before we go into assembly constraints, let's review constraints in the context of solid modeling. Recall that in solid modeling, if we want to model a part, we must first decompose that part into features or primitive shapes, and then sketch 2D profiles of those features independently before sweeping them out into 3 dimensions. Also recall that each 2D sketch should be completely defined, otherwise changes to our design might have unknown results. For instance, in this sketch, we must define the radius of the semicircle and the length of the lines, as well as a tangential relationship between the semicircle and the vertical lines, and so on. In doing so, we are applying constraints to remove degrees of freedom. Some of these are dimension constraints, and others are geometric relationship constraints that, together, control the size, shape, and orientation of entities in our 2D profile. Here's another example of a 2D profile made in Autodesk Inventor, where we have 4 dimension constraints and a bunch of geometric constraints represented by all of the symbols to fully constrain the profile. Luckily, Inventor applies a lot of these geometric constraints automatically to the entity at the time of its creation, so we only have to specify some of these manually. Overall, our goal is to fully constrain our sketch, which is equivalent to reducing the sketch's degrees of freedom to 0. We previously learned about degrees of freedom of common sketch elements like lines, circles, arcs, and ellipses, which determines how many constraints we have to apply to a sketch to fully constrain it. So let's translate this into assemblies. In assemblies, we are no longer interested in the degrees of freedom of 2D sketches used to make parts, but rather the degrees of freedom of 3D solid models that are used to make the assembly. The degrees of freedom of a 3D solid model are different from those of a 2D profile, so we must be careful not to mix them up. Consider this pin as an example. Assuming that it is a rigid body in free space, it has 6 degrees of freedom. 3 degrees of freedom in translation along the X, Y, and Z axes, and 3 in rotation about these axes, which have special names of roll, pitch, and yaw, respectively. When a solid model instance is initially brought into an assembly, it is unconstrained, meaning that all 6 degrees of freedom are open, so the object is free to translate along or rotate about any combination of these 3 coordinate axes. If we have 2 instances in an assembly, then we have 2 times 6, or 12 degrees of freedom, and so on. In assembly modeling, applying assembly constraints to relate one component instance's position relative to another can either partially or completely remove its freedom to translate or rotate. As before, these can be dimensional or geometric constraints, and in Inventor we can visualize the degrees of freedom remaining for a part by going to the View tab and selecting the Degrees of Freedom button, which will show each degree of freedom remaining as a green arrow. Here we have a single part that has been placed in an assembly, and it still has all 6 degrees of freedom based on the 6 arrows that we see. In this case, the component instance is the first part in our assembly model, so there are no other parts for us to constrain it to. We call this first component part our base instance, or the parent part, and because there are no other parts for us to constrain it to remove degrees of freedom, we have to ground the part instead. Grounding a part removes all 6 degrees of freedom. And now when we place additional component instances into the assembly model, we can constrain them to this base instance. For example, we can insert this top part into our base instance to eliminate some degrees of freedom. Specifically, once we insert it here, it will no longer be able to translate in any direction or rotate in the X or Z direction, but it still will be able to rotate about the Y-axis. So we may have to apply another constraint to remove that degree of freedom, such as aligning one of its faces with the face of the base part. Generally, there are 3 common assembly constraints at our disposal, the first being an axial alignment constraint that aligns 2 objects along some common axis, as we saw in the last example. And the second is the mate relationship constraint, which essentially sticks 2 faces together with their normals aligned in opposite directions. We also saw this in the past example. Finally, there is the planar relationship that places 2 faces flush to each other, meaning that their faces are aligned with their normals facing in the same direction. On this slide, we have all 3 types of constraints applied: the axial constraint to align the rightmost holes, the mate constraint to mate the top and bottom faces of these parts together, and the planar constraint to make the 2 yellow front faces flush with each other. You'll see these same general constraints in Inventor, although Inventor uses slightly different terminology, and we will finish off this video by going over this terminology. To start, Inventor's first constraint option is a mate-mate and mate-flush constraint to align part features. There are different options for this constraint that essentially allow us to perform a mate relationship, a planar relationship, or an axial relationship. The face-to-face option gives us the mate relationship, the flush option gives us the planar relationship, and the axis-to-axis option gives us an axial relationship. 2 additional constraint options available in Inventor are the angle and tangent constraints. As the names imply, the angle constraint will allow you to set an angle between faces, edges, or axes of parts, and the tangent constraint will allow you to make the curved or planar face of one part tangent to that of another. Finally, Inventor has an insert constraint, which is really just a combination of the axis-axis and face-face mate constraints that we saw a couple of slides earlier. This constraint is especially handy when you are inserting a bolt, a pin, or a screw into a hole, since it combines the 2 constraints together, and it also gives you the option to lock the rotation of the inserted instance as well. These are all constraints that you'll become more familiar with after watching this week's lab video. For now, this marks the end of this video on assemblies, degrees of freedom, and constraints, so stay tuned for the next video on assembly drawings.